So why continuum mechanics? Why continuum mechanics? The reason here is that we assume that our material is continuous. It's a series of continuous systems, no defects. That's why you come up with all these theories. But we won't go in depth to that concept. Anyway, the things that we have discussed should be already sufficient for you to start, whether you're doing it on a project or probably you're going to be a junior designer when you go to work. Take note that in some companies, they would prefer you to start, especially multinational companies wherein the top scientist or top engineer there, principal engineer there, or chief engineer are really hardcore mechanics guy. They would prefer you to start first with analytical solutions before doing any finite element solutions. Goodrich, they're making the nacelle of a plane. They're not using finite element really to start their design. They're just using hand calculation. So in any way, that's why it's really important if you're going to this type of company as a designer, as an analyst, is to really have at least a solid background in mechanics. Finite element is quite easy. Draw a figure, put in some fixed thing there, put in a load, you get pretty pictures. The question is, how do you know your results are correct? Again, you go back to the basics of solid mechanics. So it's always best to start your design or your calculations using the elementary mechanics theory before proceeding on to a more advanced tools. Okay, we've done this one already. So yes, just to have a go at strain hardening. So as you can see, plasticity starts after yielding. So you will also have a criteria for yield. Normally, the criteria for yield that we use will be this von Mises stress. So when that von Mises stress, okay, exceeds your yield strength of the material, then you know that your material have yielded. You are now in the plastic region. So after you reach that yield criteria, you will now be in the plastic region. Sorry, I wonder if that can be opened. Can we open that? Careful with that. Is this classroom better than the lecture theater?
Yes.
Same. Lecture theater is better. Okay. Well, there's quite a trend now that they're trying to move away from lecture theaters because they want more learning rather than teaching. Because the argument there is when you play a musical instrument, you don't just learn by looking at somebody who plays a piano or a guitar. You have to do it. If you're an athlete, then of course I'm not an athlete. Don't look like an athlete really. So if you have that, you have to practice to be able to improve your performance. So it's the same thing. I mean, that's one thing that's been going on at the moment. Glasgow is moving towards that. And I think, have you participated in that survey? No, they didn't call you? Okay. Glasgow is moving towards that. NTU, NUS is moving towards that system. And I think a lot of universities are moving towards that system. I went to a conference about learning and teaching as well, and this Stanford professor, or one professor there when I presented my paper was telling me to come up with a video. And then one professor from Stanford said that in Stanford, you get sued if your video doesn't have subtitles. So it's a requirement over there. It's cool, isn't it? Well, that is, of course, you're a lecturer or teacher. So yes, we're moving towards that, and probably we will be seeing a different setup in the future. Okay, moving on. Are you comfortable at the back now? You okay? Thanks. So, when does plasticity starts? Plasticity starts after your materials yielded. That's when you have plasticity. Well, previously we mentioned it's just important for manufacturing or manufacturing engineers. But in some cases, it's also important because if you want to stretch the application of your material a bit, you may want to know until when, after that elastic region has been reached. So that yield criteria is your boundary between elasticity and plasticity. Yield criteria. In our case, our criteria, so meaning there can be a lot of criteria, but in our case, our criteria will be using the von Mises yield criteria. When our stress reaches the von Mises, then we know that our material has yielded. Okay? So, sorry, when the von Mises stress is greater than the yield, then we know that our material has yielded. Okay, so I'm trying to just repeat myself here. There's so many equations about the curves and so on. We'll go through that later. So I'll just try to talk and talk myself until you're all tired, so please bear with me. So you have all of these. Again, the other thing that you have to do to understand is your deviatoric stress invariance. So previously, for this one here, we have our stress invariance I. So what if we remove that hydrostatic stress component? We will be able to get your deviatoric stress invariance J. And this J here, J2 here, will be important later for your failure criteria. So you can go reading in your notes. But anyway, what I'm saying here is that you will have a stress invariance J for your deviatoric stress. So that's called deviatoric stress invariance. So of course you can also use this one here. Not a problem. So here is just using the principal stresses. Yes, we have done the plane stress, plane strain assumption. So that's quite useful. We have already tested that. Right? You have the different types of loading. Uniaxial, biaxial, triaxial, torsion, and so on and so forth. Right? So this one is uniaxial, biaxial, meaning inside. Why biaxial? Because inside there's a pressure, so that stretches your small material along the longitudinal and along the transverse or hoop in this case. We know how this works already, so you can look into your notes. This one as well, if you have pure torsion. And then we have looked into these pressure vessels already. Right, so here we go. Theory of plasticity. So the thing here is that if you have, say, a polymer straw, you probably have played with your straw and stretched them out, yes? So for some reason, when it's stretched, say you apply a force A, right? If I wanted to stretch that more, what happens? do I need to apply force A or a force greater than A? So I need to apply more force greater than force A, yes? Meaning that my material hardened. So there is a strain, there is a work applied. So to be able to stretch that further, I need to apply a higher force. That's the principle of strain hardening. So we will be looking into this one later. So there you go, that's the initial yield. So this is where you have now your hardening, work hardening, so-called, or strain hardening, because once you apply a stress here, okay, the material hardens because it's strained. To be able to further strain that or stretch that, you have to apply higher stress or higher force. Okay? So once it's reached the maximum value, the ultimate strength, then that's where this one now starts to break. Yes? So this is what I say. This one separates our theory of elasticity and the theory of plasticity. Then again, are we going to study this one when it starts to crack? Not anymore, because it doesn't matter anymore, because we know the material is going to fail. So not much work is being done there. We just want to know how this material behaves from this until that. Okay, meaning we're trying to maximize the use of that material. So here, because we are already in the plastic region, so this is your stress strain curve. Yeah? So when did we have, say for example, that will be our yield criteria, wherein we have yielded already, our material have yielded. Yielded meaning doesn't fail yet, just yielded. Theory of elasticity, right? Wherein you have now your stress to be directly proportional with the strain. Because they are directly proportional, to equate them, we need a proportionality constant, E. And that E is actually our Young's modulus. So this one is called your Hooke's law. Yeah? So, after you reach this one, this Hooke's law, or this constitutive equation, doesn't work anymore. It has to be a different theory. But of course, you can always you can base your theory based on what you have with the theory of elasticity. Doesn't mean that you're going to throw away all the things that you have learned in the theory of elasticity. We're just adding knowledge to that. So, first statement: the theory of plasticity deals with the behavior of metals at strains where Hooke's law is no longer valid. Plasticity is concerned with predicting the safe limits for use of a material under combined stresses, i.e. the maximum load which can be applied to a body without causing excessive yielding, plastic flow, fracture. Continuing, so if this will be your SU, we would like to study from here to here. We're just trying to maximize the use of our material. That's what this one says. excessive yielding, plastic flow, fracture. Plasticity is also concerned with understanding the mechanisms of plastic deformation of metals. Why? Because of shape forming. Well, we have a lot of applications for shape forming because steel in itself can also be processed to be able to be used for a lot of applications. Once you form steel, then basically, or aluminum or other similar material, then it has to undergo plasticity, and that's the reason why we also have to understand plasticity. Well, up to a certain point, of course, we also want to know how we can maximize the use without reaching this one here. Because after this one, your material will fail. It doesn't make sense anymore studying this one. So it's just up to this one, just before that part. Right. Quite a lot of things here. Please try to read. It's up in your slides anyway. So here are the 4 things that you must know in the theory of plasticity. Take note, we won't be really going into depth in theory of plasticity. I'm just going to explain the things that we need to solve a few more problems, and that's it. We're going to finite element hopefully next week. Right, things that you have to know. 1, yield criteria. Right? Yield criteria to define specific stress combinations that will initiate the non-elastic response. Elastic response, of course, is before that yield, and after that, of course, plasticity. So we have to have a yield criteria. When will your material yield? That's the question. Right? So first thing, flow rule. A plastic material constitutive equation. So we have our constitutive equation for theory of elasticity. Stress equal to the stiffness multiplied by the strain. Of course, if you're just looking at 1D, stress is equal to the modulus multiplied by the strain. So for plasticity, we have an equivalent constitutive equation, and that is called the flow rule, to relate the stress to the plastic strain. Our constitutive equation is also relating the stress with the strain. So here, stress to the plastic strain. Hardening rule. Okay, to define the evolution of yield criteria, we'll explain that later. And the elastic plastic strain decomposition rule. So these are the 2 things. Probably we won't really go into depth, but we will be solving some problems regarding this one. Right. This one stuff. Have a look into this one here. Ideally, or in testing, this is what you can observe. Of course, there can also be some materials can go straight there. I mean, without this thing. I mean, here it's quite easy to identify your yield if the material will behave in this manner when you perform tensile testing. The thing is that if you have this one to be moving there, then you have to estimate that yield somewhere. Okay, probably have that in your poly, wherein you have a 2% yield. Just draw a line 2% from that, and then pinpoint that yield. Now, plasticity would like to come up with a model wherein you want to imitate or you want to predict this stress strain curve. So none of them are perfect. So these are just so-called models to be able to determine the stress strain of a certain material. So as you can see, one there, the first model there is the rigid perfectly plastic. wherein you assume that this one goes there and then goes plastic. That's the first one there, up one. So this one, the model here, of course, is not plastic. There you go. It's not perfect. The other one, of course, is the elastic perfectly plastic. So this one is perfectly plastic. Okay, perfectly plastic, straight line. Elastic. So you have elastic, perfectly plastic. Second one, meaning after, well, that's simple. If you have a spring, right, you will have, you will be putting in strain onto the spring. Afterwards, your mass will move. So that's before the mass moves, and this one when the mass moves. So for the first one, you just apply a force and the mass moves. For the second one, there's a bit of stretching on the spring, which is this one here, linear movement, before you have a plastic response. Okay? This one here has to do with rigid linear work hardening. So that and that, again, it's not perfect. And then finally, you have probably the best one, elastic linear work hardening, which predicts your stress strain curve to be like that. So all of these are basically theoretical models to be able to simulate your stress strain. So they are just proposed models. Rigid, perfectly plastic, elastic, rigid, linear work hardening, and elastic linear work hardening. So these ones are proposed models for plasticity. Yes? So that's one. Idealized, meaning that you probably want it to be like that. Reason, it makes calculations simpler. Why do we have models? Because we want to have a representation, or we want to predict what's going on. Doesn't have to be perfect. At least it gives us an idea. That's the second one. As you can see, still not, but some would like to just simplify their solution and have it this one, and then you have that. Still the best or the most difficult of the models, but still not perfect. Okay? So here we go. Let's have a look at this one here. In uniaxial tension, yielding occurs when your stress is equal to your yield stress or yield strength. Again, really, I'm just following the notations in your book, but this one should be just SY. But since I'm using the notations from your notes, so this one means that when your stress reaches your yield strength, then your material will yield. The question is, what is your stress? So in our case, our stress is the von Mises stress. So when the stress reaches the yield stress, then you know that your material has yielded. Hydrostatic pressure that does not cause yielding. How about that? Why is that so? Yielding. Yes? Because it's compressive. Maybe doesn't cause distortion because your hydrostatic stress is just trying to change the volume, not the shape. Experiments in multi-axial stress state shows that if sigma 2 or sigma 3 is large enough, then yielding will not occur until your principal stress is much larger than your yield strength. We'll prove that later. Okay, so these are the things that you have to, we will be able to prove that. So have a look at this hydrostatic pressure does not cause yielding. Why is that so? They are all equal. Have a look at this one here. Your von Mises. Sigma 1 equal to sigma 2 equal to sigma 3. What do you have? Look at your, oh, it's not here. Yes? What if you have your, let's say, sigma ij principal? Sigma 1, sigma 2, sigma 3. So if you have a perfectly hydrostatic stress state, what happens? Your sigma 1 equal to sigma 2 equal to sigma 3. Let's have a look at our von Mises stress. Because this being our failure criteria, what happens? So what's this value? 0. Because your hydrostatic stress just changes the volume, not the shape. So what changes the shape will be your deviatoric stress. Yeah. What does this one say? Now that we have proven that if we have a hydrostatic stress state, wherein it won't yield, what does this mean? So if you just have a uniaxial loading, right, uniaxial, then you will know that your material will yield once your applied stress is equal to the yield strength of your material. In this case, you have sigma 2, sigma 3. High, sigma 2, sigma 3, multi-axial stress, large enough. So you have 1, 2, 3. So you're trying to, what you're looking here is that you have high stresses in 1, 2, 3 direction that you're trying to achieve a so-called hydrostatic stress state. So that to be able to yield, you have to have a very, very high sigma 1. So have a look at this one here. This one here, yes? And that one there. So you're looking at the principal stresses. You're not looking at the complete state of stress. You're just looking at the principal stress. So if they are high, probably, yeah, any value there. So just compare this one here. That you're basically high enough, meaning that you have almost the same values that you're trying to achieve already this hydrostatic state of stress. So this one, okay, will require a very, very high sigma 1 to be able to cause yielding. We'll have those examples later. At the moment, have a thought of these things that you may want to look at. Failure criteria. 1, 2. Okay, we didn't discuss shear failure criteria, but shear is another criteria wherein you can simply calculate that. So this is your maximum principal stress criterion. You have your axis sigma 1, sigma 2. Yes? So what you're going to do is, this one is sigma 1, draw a straight line, sigma 2, and then you have a rectangle. Sigma 1 and sigma 2 only. So if this is your graphical representation of the maximum principal stress criterion, then you have this one to be your safe zone. Okay, so you have your axis sigma 1, sigma 2. That's your principal, your value for your principal stress 1, value for principal stress 2. Then you draw that square or rectangle. So this is the so-called safe zone. Okay, so if your sigma 1, if you're somewhere here, then you're failed, right? If you're somewhere here, then you know you're safe. So that's the meaning of that. Meaning that if your sigma 1 is here and sigma 2 is here, then you're somewhere here, then you're safe. You're within the safe region. This one is for the maximum principal stress criterion. Again, we have a lot of failure criterion, so it's up to you really to decide which one to use, depending on the type of material, depending on the type of loading you have. The maximum shear, okay, is just this one here. So not a problem. You just calculate the maximum shear, get the maximum, get the minimum, divided by 2. That's your maximum shear. And how do we graph that? So anyway, these are all calculations. So there you go. This is your safe zone. Okay, you have your sigma 1, sigma 2. This is now your safe zone. Okay, maximum shear criterion. It's not normally used. It's not normally used, but this is one of the criterion if your material is loaded in shear. The other criterion is the von Mises stress criterion. Okay, so you can read on this one here of the hedral shear stress and so on, so you can derive your von Mises. So there you go. So your von Mises stress criterion is this one here. So we put all of these 3 stress criterion or failure criterion together. So this one is your maximum principal stress. This one is your von Mises, and this one is your shear. So they will have a common zone. They will also have different zones. So again, depending on your application, you must state your assumptions. Which failure criteria you're using. I guess you're all doing FYP. Somehow some of you will have relations to design, right? So after you calculate the stress, what's next? Some will just show pretty pictures and that's it. Ask the student to explain nothing. Okay, so after that, of course, identify a failure criteria, determine whether your design will fail or will be safe. So this is your failure criteria. Principal stress, von Mises, and your shear criteria. How does all of this compare with test? So again, it's so easy to come up with all these theories really. Come up with a graph, come up with a figure. Very easy. And say that, oh, actually they matches. But the thing there is you have to convince yourself, or people have to convince themselves, that the values or the theories that you're proposing must match that of the test data. So we have here, what do we have here? Cast iron. So as you can see, some of the materials here fall within the von Mises or fall within the principal stress. So again, here are the differences. Differences is less than 50%. Tresca, which is the shear. Von Mises, applicable for ductile metals. So this is what it's saying. Know your materials. That's why you use the CES software. You don't just use the CEF software, click here, click there, you come up with all this lily pond, as what the author says. So the person who actually developed that was here in Singapore last year. A very nice chap from Cambridge. Very nice, very passionate about coming up with lily ponds and all. So he developed the CES software plus the lecture notes probably that you're using. Okay, so passionate about that. Right. So you have to come up with this, you have to know your material. Ductile metals. In this case, as you can see, Tresca and von Mises applicable for ductile metals, difference less than 15%. Okay? If you can recall in Mechanics 3, you did some modeling and then you compare it with the actual test data. As long as the difference is 10%, then your solution is so-called correct. If you can remember that. Okay? It's so difficult to achieve 1% or 5% match with reality, really. Because in theory, we have so many assumptions. So we're hoping that in a very ideal world that all of this will happen because of our assumptions. Unfortunately, that doesn't happen in reality. So our calculations are all based on perfect assumptions. Why? Because it makes it easy to come up with the simple equations. So we accept 10%, 15%, as you can see. So here you can use the shear stress and the distortional stress theory, both applicable for ductile metals because of the test data. Difference less than 15%. Tresca, slightly more conservative because its safe zone is smaller than the von Mises safe zone. So a bit conservative, but not really that conservative as compared to the distortion theory. And so ductile for von Mises, brittle for maximum normal stress or principal stress. So know your material, know the type of the material you're using. Yes, before you even try to apply your failure criteria. Okay, so these are just some yielding criteria that you can have a look at. Please go on and read those. Again, what I said was this J2 thing, which is the more important thing, but we won't be really going in depth into this one. What it's saying is just that when you reach this value, then you know that your material has yielded. So nothing more. Okay, so please go through that. That's additional information that I placed there. Right. So what we're looking now in plasticity, so you have this curve already, yes? So this is your elastic plastic curve. You have this one to be the elastic region, and this one is the plastic region. So now when we go to elasticity, we determine the yield criterion, and then we cut it. Cut there, you have now your plastic stress strain curve. Yes? This is now your plastic zone. So after you determine your yield criteria, identify your yield criteria, you cut that. And this is now your stress strain curve. And this one will be your yield. So this one now is just purely looking at the plastic region. Okay, so have a 10 minutes break.